ionization energy. And I said that we had these general trends. You are responsible for these general trends. Trend is that, or sorry, first off, what is ionization energy? Okay, it's the energy required to take the electron that's attached to the atom and completely remove it. Okay, well, if we go back to our energy diagrams with our lines, okay, we said the minimum was our energy level 1, so we call that 1, and the maximum is when it's not attached. It says attached. If we take an electron and move it all the way up to there, what happened? That electron had to gain in energy. How does it gain in energy? We give it to it. Okay? It's the energy required to move that electron, the energy that that electron needs to absorb to shift all the way up. Okay? So that's what's happening in that transition. If we go through and look at our general trends, within a column, it increases as we go from bottom to top. Well, why might it increase as we go from bottom to top? What's changing as we go from the bottom of the periodic table to the top? It's the electron configuration for hydrogen. Crap, it's erased. It was 1s1. When we go within that column, 1 down, what happened? Same configuration, but second energy level. So now my electron is here. Is that going to require more energy or less energy to get ripped out? Less energy. It's closer to it. That distance is effectively an energy. So if we take a look at our lowest energy electrons, hydrogen, the amount of energy required to rip that out is going to be more than the amount of energy to rip it out of a lithium, because it's starting at a lower energy. We get a bigger energy difference. Okay, so it's looking at the energy levels. That trend tends to make sense. Kind of matches the same idea with our atomic radius. As we move down a column, what happens to the radius? Not that I'm giving away the answer by moving my hands. It gets bigger. Why? We're putting electrons into higher energy levels, which need to be further away from the nucleus. Why is it higher in energy to be further from the nucleus?
Because the nucleus has a pole.
Right idea? Yeah.
Okay.
The nucleus has a positive charge.
Yes.
The closer that negative is of our electron to the positive, what happens to the effective charge?
It neutralizes.
More neutral.
Yeah.
The further away it is, the more negative it appears, because there's nothing to neutralize it. Charge is bad. Okay? Less stable. What happens when we go left to right across the periodic table? Now this one gets a little bit interesting. Okay? Just like with our atomic radius. What happened with our atomic radius when we moved left to right? It got smaller, which was very counterintuitive when we talked about it. We're adding more electrons. We would expect within that row, more electrons should be bigger, but it gets smaller. Seems really, really odd. Why does it get smaller? Where are the electrons going?
Going closer to the nucleus.
They're going to the exact same energy level. Within a row, that's all the same energy. So if they're going into the same energy level, we aren't changing the size. What else is changing when we go left to right? What? Of what? Okay, the electrons, but we're saying we're putting all the electrons into the same energy level. That shouldn't change the size. What's happening in the nucleus? There's more protons. The larger the positive charge, what's it going to do to the electrons? It's going to pull them tighter in. So what ends up happening is our radius shrinks. Okay, because we're putting all those electrons into that same energy level. Same distance away, but now a stronger nucleus. The electrons get pulled tighter. What's happening with the ionization energy is a fairly similar concept. As we go from left to right across the periodic table, it increases. Why would it increase? Okay, what happened to the radius as we went from left to right? It decreased. If it decreases, what are we doing to the effective stability of those electrons? Putting them closer towards the nucleus, closer towards that lower energy level. So as we go left to right, we decrease the radius, and now make it harder to rip that electron out because it's now closer to the nucleus. So it actually makes sense. We're putting our electrons closer to the positive charge. It's going to make it harder to rip it out. Okay? There's a caveat with these explanations. Notice that in both of these cases we say in general. Okay, whenever you see in general, you should kind of go, oh, something ugly is about to happen. Okay? What is in general implying here? There are exceptions. Okay? Up to you on how you want to remember these exceptions. There's a reason we talked about the electron configurations, because the electron configurations explain the exceptions. So you either memorize the exceptions or you understand how to draw electron configurations, and there's nothing to memorize. Okay? So what do I mean? Let's take a look at some of those. So helium, neon, argon, krypton, xenon, radon. What happens to the ionization energy? Okay, we start with helium way up top and radon down below. Our energy increases. What happened to the energy? It decreased as we went from helium to radon. Exactly what we would have predicted. If we look at transitioning between, now we're going to have to shift to a lower row, lithium to neon. What's the overall change? It increases. That's exactly what our trend said. So what we want to do now is actually go back through and pick one of those and say, is it always true? Well, what's the element after lithium? Beryllium. There's only one way to go. Left to right, beryllium. Next element? Boron. Huh, interesting. Lithium to beryllium, energy went up. That makes sense. Beryllium to boron, energy went down. First exception. Why is that happening? Well, go to the electron configurations. The electron configuration for beryllium, 2. This was our beryllium. How about for boron? 1s2, 2s2, 2p1 for boron. Why might it be easier to remove an electron from boron than it is from beryllium? What happens if we rip an electron from boron? We get lots of symmetry. Okay? If we rip one away from beryllium, we lose that pairing. So it doesn't particularly like that, which is why it's higher in energy than with lithium. Okay? But when we look at boron, we see that big drop because that one electron is actually making boron unsymmetrical. Okay? So if we're going to look at its ionization energy, it's going to say, I'm going to get rid of you pretty quickly because I don't want to deal with you. You make me look ugly. Okay? So that's kind of the idea behind it. We can look at our electron configurations and evaluate our symmetries. What's the next element after boron? Carbon. That goes up. That makes sense. Next one. Nitrogen, again, goes up. Makes sense. Next element. Oxygen. That went down. So what do? Yep, I'm listening.
What made it go? Okay, I'm looking at the numbers, and I'm seeing 7 to 8, and then I'm seeing the mass is 14.01 to 16. So what made it go down? I don't understand.
Mass has nothing to do with it. Mass has to do with the nucleus. What we looked at was the electron configuration.
Okay.
So you're correlating two entirely different things. Mass has nothing to do with electrons. When you're looking at energies, we're looking at ionization energy. Ionization energy is the energy to do what? It's actually up there. To remove what?
Remove an electron.
An electron. Does the mass have anything to do with electrons? Nope. Do not start shuffling your concepts. You have to know the definition. Your ionization energy is purely for electrons. Mass is irrelevant. Okay? What you would need to look at is where the electrons exist. Okay? And the energy levels of those electrons. How do we describe the energy levels of electrons? Where do our electrons live? Outside the nucleus in energy levels in orbitals. So we have to look at our electron configurations and have an understanding of those energy levels, which is why we keep going back and forth between that line diagram and the electron orbitals, okay, and our electron configuration argument. So if we take a look at nitrogen versus oxygen, should I draw the electron configurations, or you got a question that's dying to come out?
Oh, no, keep going. I'm
Okay.
trying to think about it as I'm raising my hand.
Okay. So let's take a look at our nitrogen versus oxygen. So remember, we now said mass is irrelevant. It goes to electrons.
Okay.
How many electrons does our nitrogen have?
7,
7. How do you know it has 7?
because it has 7 protons.
7 protons. At this point, we haven't talked anything about charge, so it's exactly the same number, protons, electrons. Okay? So we do our electron configuration, 1s2, 2s2, 2p3. Why do we know 3? 2 plus 2 plus 3 gives us 7, the 7 electrons we're supposed to put into it. Okay? Next one we got to do is oxygen. Electron configuration for oxygen. 1s2, 2s2, 2p4. Huh. Interesting. Do you see anything to do with symmetry in this case? I don't see anything obvious. Remember we said that whole orientation thing, wrapping things out as x, y, and z, the px, the py, the pz. And I said it's not that important, but it's kind of important. Guess where it's important? Right now. Okay? So instead of looking at it as just our P3 and P4, let's look at what those P's break down into. We get PX, PY, and PZ. In the case of nitrogen, where do those 3 electrons go? 1, 1, 1. Because they're all at the same energy level. We're only allowed to pair up if we have to jump to a higher energy level. We don't jump to a higher energy level. These are all at the same energy, so those are half filled. Why is that interesting for nitrogen? These are now all half-filled orbitals. That's pretty symmetric. If everything is 1, that's symmetric. What happens when we jump to oxygen? We now have to double up, and we would put 2 electrons in there. What happens to the symmetry? We lose the symmetry. So oxygen takes a look at this and says, if I get rid of 1 electron, what happens? I'm symmetrical. So what happens to its ionization energy? It's going to drop lower than nitrogen, because it can now get rid of that electron relatively easily and get symmetry, whereas nitrogen has the opposite problem. If we got rid of 1 electron, we make it less symmetrical. Okay? So the idea is to use your electron configurations to predict the energy levels that we can see, or the energy differences. Okay? Do you need to be able to predict with the electron configurations? For this class, arguably not. What do you need to know instead? The trend. You know the trend, you'll get most of the points. You don't know the trend, you need the electron configurations. That is a more challenging question. If you're trying to get an A in this class, you need to know how to explain that. Okay? Questions? Okay, you guys both had questions.
Well, I'm lost now, so that's okay, I'll come.
Okay, we'll come back to it later.
That actually explained it. I forgot that I get 1, 1, 1, and not 2, 2, 2. So that's what I was confused.
Yep. Okay? So that's what's happening with our ionization energies. So people wonder, why do we look at electron configurations? Because it explains physical observables. Every theory that we come up with in chemistry does something to explain a physical observable. That's why we made them theories and why we make you pay attention or memorize them. Okay? Because there's an understanding behind them. Okay? What charge does the atom become if we look at the ionization energy? So what was the definition of ionization energy? Removes an electron. If we remove an electron from any atom, what happens to its charge? It's going to become positive because it lost a negative. So minus a -1 gives us positive. Okay? Again, this is going to become relevant here in just a little bit. This is something the textbook left out, and kind of understandably, because it's easy to get it confused with the ionization energy. So you don't need to write anything down necessarily on this. We'll just briefly talk about it. The electron affinity is the energy released to grab an electron from the vacuum. How does it relate to the ionization energy as far as the definition goes? What was our ionization energy? Remove an electron. What's the electron affinity? Accept an electron. Okay? We're looking at opposite processes. Is that a word? What charge does the atom become if we look at electron affinity?
What charge does the electron become?
What charge does the atom become if it accepts an electron? Plus a negative charge gives us negative. Okay? So when we're looking at the electron affinity, it's a very similar process to the ionization energy. And we can use both of these concepts in collusion to kind of come up to a new concept, which we'll look at here in just a second. So why do we mention both? Okay? We mention both because together they represent something known as the electronegativity, or can be used to help define this. Okay? Massively important concept. I cannot stress enough how important electronegativity is to chemistry in general. Okay? It applies in organic chemistry, applies in biochemistry. Everything that you are going to do in any chemistry class comes down to the electronegativity. Okay? We may hide it and say it's not really that, but it is. Okay? So what's happening with electronegativity? Linus Pauling went through and tried to come up with an understanding of how and why atoms did different things. So at this stage in the game, we don't understand why we get a particular formula we get. Okay? We just know we've got it, and that anything within that family does similar chemistry. Okay? But we didn't understand why. Okay? So Linus Pauling kind of thought about it, and started to look at the patterns that he saw. Okay? And one of the big patterns that he noticed is that fluoride, chloride, bromide, and iodide, sorry, I should say the element, fluorine, chlorine, bromine, and iodine, all, when they ionized, became negatively charged. It's kind of odd. Why would they all become negative? Well, maybe all elements become negative. So we look at lithium, sodium, potassium, rubidium, cesium, francium. Why not? What happened to them? They all became positive. Wait, why would one become positive and one become negative? There's got to be something going on with their overall natures to explain this. Okay? That ultimately comes back to electronegativity. Okay? So electronegativity is the ability of one atom to take bonding electrons from another atom. Okay? So it is different than your ionization energy and electron affinity because we're looking at bonding electrons, not electrons in a vacuum. Okay? Within this trend, he found that fluorine is the most electronegative and cesium is the least. Okay? Have we seen another trend where we get this kind of polar opposites on those corners? Metallic characteristics. Cesium is the most metallic. Fluorine is the least. Okay? Another interesting thing that he noted with it, if you take a look at that last column, are noble gases. Okay, it's kind of hard to see on this, but what are they? What's their height?
Like flat.
Flat. Whereas fluorine's really, really tall. Why is fluorine tall and then all the noble gases have nothing? Well, they aren't even positive. What happens to fluorine if it steals an electron from another atom? So let's take a look at fluorine real closely. Fluorine, electron configuration 1s2, 2s2, 2p5. If it steals an electron, what charge does it become? Negative, so we can call it F minus. Where is that electron going to go? So we put in electrons in, and we put our electrons always where? The lowest energy level possible. Can we put it into the 1s orbital? No, why not? Already 2. How about the 2s? No, already 2 there. How about the p?
Yes.
Yeah, I can put 1 there. Okay, cool. So there we go. 2p6.
But then it's not the original fluoride.
So the electron configuration is not fluorine, and that's why it's F minus. We've changed its charge. It still has the same number of protons.
Okay, and is that where we put the minus when we write
And
it?
that's where we would put our charge. Remember when we did our electron configurations? Where did we count our electrons? Upper right-hand corner. Translates to our elements too. Okay. Why is this configuration interesting? Is there another element that has this configuration? Is there another element that has 10 electrons? Yeah, what element is that? Neon. What type or what column is neon in? Don't tell me the last one. Our noble gases, also known as, remember this one? Fancy weird word with an I? The inert gases. What did inert mean? Not reactive. Remember our noble gases, hoity-toity, floating off on their own, don't want to react? Fluorine tries to make itself look like a noble gas, because if it does, it now has that same hoity-toity characteristics that our noble gas did. So if you think about us in our class systems, okay, everybody wants to be rich, so what do? Buy nice clothes, we buy a nice car, even if we can't afford them. Why? Because it makes us feel rich. Okay? Our elements are doing the same thing. Okay? They are accepting those electrons to push up and try and look like those noble gases and exist like them. So that explains fluoride gaining an electron, because it starts to look like the noble gas neon. But what about our metals? Might regret this, but let's go ahead and do sodium.
I just have a quick question.
Yes, fire away.
That makes it negative, adding an electron.
Yes.
So then what would give it a positive charge?
Let's take a look at it right here. 1s2, 2s2, so we're looking at sodium, then it would be 2p, 6, 3s, 1, 1, 1, there it is. Okay. Sodium, we said, or Linus Pauling found, wanted to become positive. How can it become positively charged? Okay, well, we can't change the number of protons, because if we add a proton, it's not sodium anymore. It becomes... What element does sodium become if it gains a proton?
We take one away so that it becomes like neon.
Right idea, wrong question, though. If we add a proton, what happens to sodium?
It turns into a different element.
Becomes magnesium. Now let's go back to our electron count. So we can move our electrons without changing the element. What happens if we remove an electron?
It becomes positive one like neon.
Okay, if we lose an electron, that's minus for loss of an electron, which is negative. The double negative gives us our positive. The charge on sodium becomes positive. Why is that important? What happens to our electron configuration? Holy junk, what did it turn into? It turned into neon. Again, neon being our noble gas. Okay? So our elements, their electronegativities can help us predict how they're getting to these charges.
So are
Okay.
they all trying to become like noble gases? Like whichever one is closest to the
Exactly right. So I have a question about closest. So let's take a look at our charge system. So what we just went through and did is defined isoelectronic. Same electrons is isoelectronic. So sodium ion, was it sodium ion? Sodium ion, Na plus, is isoelectronic to neon because they have the same electron count. Okay? You said closest. I see sodium here, and I see neon over here. There you go. Don't envision the periodic table as a flat surface. Wrap it. Put it on a cylinder. Okay? That sodium ion now starts to get pretty darn close to our neon. Okay?
It's easier to go one backwards than like...
So that's going to be the next question. If we want to get to be a noble gas, okay, sodium can become like neon or like argon. How do we get sodium to look like argon? So where's sodium? Here, right? With 11 electrons. To get like argon, we need to add electrons. We would have to add 3, 4, 5, 6, 7 electrons to make it look like argon. How'd you do the 7 that fast?
That would make it a negative, and then to make it.
Wait for it. Take the number of electrons we're trying to get to minus where we start.
Subtract it.
18 minus 11 gives us 7 electrons. What charge would that become?
Negative.
Negative what? It gained, so plus 7 negative species. So the charge becomes negative 7. Okay? So the next question is how? Sodium wants to look like a noble gas. If it looks like neon, what does it do? Loses 1 electron. If it looks like argon, it has to gain 7 electrons. Which is easier? Lose the 1. So sodium becomes plus 1. Magnesium. Magnesium can look like neon or argon. To look like neon, what does magnesium need to do? Lose 2 electrons. To look like argon, it needs to gain 6. Which is easier? Lose 2, gain 6.
Lose 2.
Lose 2. What happens to magnesium?
Like neon.
Plus 2 charge. We can predict its charge based on how it can start to look like our noble gas electron configurations. Okay? What happens when we move over to fluoride? It could look like helium or neon. To look like helium, what does it need to do? It needs to lose 7 electrons. To look like neon, gain 1. Which is easier? Gain 1. What happens? Fluorine gains 1 electron to become fluoride, our negatively charged species. What happens with oxygen? It can either gain 2 to look like neon or lose, I keep messing up the math, lose 6, which is easier, lose 6 or gain 2? Gain 2. If it gains 2 electrons, its charge becomes? Negative 2. Nitrogen.
How do you write that when you're doing the configuration?
You don't write it. So in the configurations, let's do it for nitrogen. Okay? So electron configuration for nitrogen. I didn't leave myself a lot of space here, so let's do nitrogen up top. Would be 1s, 2, 2s, 2p, 3. If I want to look at nitrogen having gained 3 electrons, what I'm going to go through and do is change my notation a little bit. Now it's going to show up at the bottom. So first off, we can cheat a little bit. What's the charge on nitrogen supposed to be if it gains 3 electrons? Negative 3. We would write that nitrogen minus 3. Notice where the minus 3 is getting written. Upper right-hand corner, where we specify our electric charge.
So like on a test, when you say this is the electron configuration for nitrogen, make it negative 3 charge or something like that?
On a test, I would probably say, give me the electron configuration for nitrogen minus 3. I wouldn't even give you nitrogen.
Okay.
Because you should be able to figure that out. What happens to our final electron configuration? 2p6. Okay.
I'm not sure if we even have to know this, but what about carbon?
That's the next question. What does carbon do?
Gain 4, lose 4.
Could gain 4 or lose 4. Which one's easier?
Whichever you choose.
This is a good silence question. It's kind of hard to figure that one out. Okay, which means when we look at carbon, it turns out that it gets both. It can be plus 4 or minus 4, depending on what it's interacting with. When do you think it might be minus 4? What do you think it might be bound to or interacting with? Okay, noble gases don't react, so that's a bit of a non sequitur on that one. So if we look at oxygen and fluorine, they want to be what charge? negative. If carbon were to be negative, what happens when we bring those negatives near each other? Repel. So putting our carbon near a nitrogen, oxygen, or fluorine, not the nicest option. We get that negative-negative repulsion. What's the other option? Let's put that carbon near a positively charged element, like magnesium, calcium, rubidium, pretty much any metal, and carbon will pick up that negative charge. Okay.
So are the even numbers negatively charged and the odd numbers are positively charged?
No. That doesn't make sense. You have to go based on how they get towards the noble gases. Okay. Odd number, fluorine, 9. What's its charge? Negative. Odd or even number, oxygen, 8. What's its charge? Negative. Can't go based off of your odd and even rule. Okay? It's all about how they get to look like the electron configuration of the noble gases. You have to shift to that. Okay? So if you have problems with electron configurations, what should you be doing a lot of this weekend? Practicing them, asking questions, post comments to the discussion board, send me emails, show up to office hours. The electron configurations are really important for being able to process these types of concepts. Your other option, if you don't understand the electron configurations, because there is another one, see all the elements that are up here? You know their names and their symbols, right? Guess what you now need to memorize? Their charge. Okay? So you can either understand the material or you memorize like crazy. Okay? What's that?
I'd rather understand it.
That's what I would agree with. So that understanding is going to take a little bit of practice to process and build. Yeah?
Okay, so then, but like, what kind of questions, like, why do we need to know how to do this, I guess is my.
What's the charge on oxygen?
The charge? Negative. Negative.
Negative 2. What's the charge, standard charge on a chlorine atom?
The standard charge, negative 1, right?
Okay, you just answered 2 questions.
Okay, so that's what that is. All
The
right.
next big issue that we could address.
But you're not asking for the configuration of that. You're just asking for the charge of what it is.
True.
Okay.
And if you're comfortable with the electron configurations, you can quickly and efficiently look at what you have to do to get to look like the noble gases.
Okay.
Okay.
That makes more sense.
Another question that we could ask, just because this is fun, what is the formula for lithium and an oxygen compound? You now have all of the tools to be able to answer that question, even though we haven't actually discussed that material. If I asked you for the compound that has lithium and oxygen in it,
Yeah.
what is that formula? And I'll even give you an extra piece of information. The compound needs to have no charge.
So they have to like, okay.
What happens with our formula? Well, let's take a stab at it. Let's say we bring in lithium, Li, and oxygen. What's our charge on lithium? +1. What's the charge on oxygen? -2. If this was our formula, what happens to the charge on our molecule? -1. If I need it to be neutral, have no charge, what do I have to do? Let's put in 2 lithiums. We just did a formula. You sing it, it sounds so much better. Maybe just in your head, though. Okay. So understanding these charges can get you into molecular formulas. Where did the charges come from? Electron configuration. So it again comes down to how much you want to spend memorizing versus understanding and deriving all the way back and forth. Okay.
Is that because the twos cancel each other?
No. If I have 1 lithium, it's a +1 charge. If I make it 2 lithiums, what I'm doing now is saying 2 times a +1 charge plus my -2 of my oxygen times its 1 atom gives me 0 overall charge.
But why are you putting the 2 there then? Why aren't you putting the 2 in front of the lithium if it's signifying 2 lithiums? Does that make sense? Like,
So we have talked about this before. You put the number in front, that number applies to everything after it. Remember when we looked at molecular formulas way back in chapter 3? maybe. And we wrote out individual formulas. If we put the number in front,
It means everything's times
it
2.
means everything thereafter is times 2. If we only want it to refer to the thing directly in front of it, we use the subscript, and it only refers to directly in front of it. Okay. And yeah, that is a tricky thing that's going to come back with our formulas. You have to remember how to do the notations. Okay?
That's why like H2O has to be H, two of them in order to bind
Yep.
with the
So
O.
if you look at the formula for H2O, everybody seems to remember water, right? H2O. Why is it H2O?
To make it
2 hydrogens per 1 oxygen. Why do we need 2 hydrogens? Because, oh man. Oh yeah, there it is. Hydrogen is a +1 charge. Oxygen is a -2. How do we neutralize those charges? We need 2 hydrogens. H2O. Okay? H3O is not neutral. Yeah.
Why is H +1 or -1? Like, I understand why it would be +1.
So why does hydrogen go back and forth? Again, we can go back to our electron configurations. Electron configuration for hydrogen is what? 1s1. If it gains an electron, it looks like helium. If it loses an electron, it looks like the noble gas before helium. So it matches electronically that column, but it doesn't have any electrons. So that's why hydrogen's kind of in a weird spot.
What is the noble gas?
There isn't one. It's hydrogen without an electron. Okay. It goes back to those symmetry arguments. Okay. And a completely empty orbital versus 2 electrons in that orbital. Okay. So, other things that we're going to address here. We finished chapter 4 and 5. So things to remember from chapter 4. This is effectively your study guide for these 2 chapters. Cool scientists, Dalton, Thomson, Millikan, Curie, and Rutherford. There are 2 scientists on this list that are going to be more difficult than the other 3. Which 2 are those? Millikan and... I would argue not Rutherford, but maybe you have different opinions. Okay, as a big hint, the reason why I would say they are more difficult, these 2 scientists have only been talked about in the lecture. Millikan and Curie. Okay, pretty sure the textbook did not address either of those 2 names. Okay, so you need to go back to the lecture slides to reference why those 2 scientists were important. Next thing that we looked at within that chapter was some of your subatomic particles. Where we started with our subatomic particles was protons and neutrons. Okay, why not include electrons yet? Okay. It's not even just talking about the nucleus. To understand where our electrons existed, what did we need to know information about?
Orbitals.
We needed to know orbitals. We needed to know the wave nature of light, our discrete versus continuous. Okay? So you've got the definition between those 2. Big, important thing to discuss. What's an example of a continuous spectrum? Those of you who've done the homework? Rainbow is a continuous spectrum. There's no empty space between the individual colors. Or rather, there's no individual color. They all smoothly blend from one to the other. What's an example of a discrete situation? Also known as quantized. It's the same as quantized. No, that's an interesting one. Piano. When you hit a piano, you hit an individual note. Right? An individual key on the piano gives you a single sound. I'm sure you can make that more complex, right? Yeah, so let's just leave it at that. Okay. Other simple examples we could look at. A continuous example would be a slope. Okay, just a plane. Not escalators. Whereas quantized could be steps or a ladder. Okay, we've got individual plateaus within that. Whereas on the slope, we don't have that individual plateau. I've added this first morning, didn't find it funny. I got 1 laugh, that's all I needed. Bohr was a discrete gentleman. What does that mean? What was Bohr's theory? Electrons existed in discrete orbitals, okay, discrete energies. Okay, so that gives us our orbitals, our electron homes. So where can we put our electrons? Which gives us back to our subatomic particles of electrons. Once we have electrons, we can look at configurations, our lovely electron configurations, and we can also look at our valence electrons. What are our valence electrons? The outer shell. Can we get a little more broad with that term? Or narrow? I'm not quite sure which way to go on that. Our highest energy level electrons. Okay? So that would be our bulk energy levels. 1, 2, 3, 4, 5, 6. Okay? I think that's all for chapter 4. Chapter 5 talks about the periodic table in Mendeleev. So you can do predictions based on what Mendeleev put together. Okay? We can look at trends. Electron orbitals. We talked about S blocks, P blocks, D blocks, F blocks. Okay? We've also got the chemical and physical properties based on this. So if you're given the formula for lithium oxide, can you predict the formula for potassium oxide? Yes, you should. Okay? Atomic radius, another big principle that you'll need to remember as far as how that aligns on your periodic table. Ionization energy. The bulk trends would be kind of your B level. The exceptions put you up in that A level category. And then the last one would be your ionic charges. Okay, we'll keep coming back to ionic charges. I highly, highly recommend you memorize them. Okay, or come up with some way to have them memorized. Okay, so our group 1 has what charge?
Positive.
Positive 1. Group 2. Group 3? Positive 3. Group 4? Questionable.
It could be,
Well, transitional would be positive 4.
it could be positive 4.
Yeah, it could be positive 4 and negative 4. And I said group 3. That was wrong. Sorry. 13. Group 13 is our plus 3. Group 14.
Plus or minus 4.
Plus or minus 4.
Negative
Group
3.
15.
Minus 3.
Minus 3.
Minus 2.
Minus 1.
0. So guess what you already did? Or at least some of you did. You now have them all memorized. Okay? Everything within that column is going to match that charge. So that's kind of a nice trend to pick up. Oh, I forgot. So, quiz. Here we go. I'm going to give you 3 minutes to work on this. So you can look at it, think about it while I'm passing out little quiz sheets. Since you're only getting 3 minutes, think about it long and hard. You can use your notes. I lied. Never mind. I didn't cut paper. So there's not enough paper to do a quiz. So we'll shift away from that. Let's try that again. Yes, I will give you 3 minutes right now to go ahead and try it on your own. If you got questions, talk to the people around you, raise your hand. I'll come through to help you out as well. Recording. Did want to talk a little bit about bonding. Really what I want to talk about is kind of with our homework. The homework is currently organized how I thought I was going to lecture on it, and I changed my mind. We've got chapter 12, where we're going to talk about some ideas of bonds, look at ionic bonding, then look at chapter 6. Chapter 6 is all about naming. So we start with chapter 12, yay, ionic bonds. Now chapter 6, how do we refer to those ionic bonds? Can we name that compound? So we don't run around saying it's BeO. Okay, we have to come up with a name for it. Then we'd move back to chapter 12 to look at covalent bonds. And we move back to chapter 6 to look at the naming of covalent bonds. And then what's not on this list, because I ran out of space, is moving back to chapter 12 to look at how these objects are shaped. All of these questions have already been posted to Canvas under the homework 2 for exam 2 thing, announcement.
Is this the same where we don't have to write out the question?
You do not have to write out the question, just the answer. All right. So, chemical bonding. Get into some brief ideas on what's happening with this. We take two atoms and we bring them near each other. What makes it a bond? That doesn't necessarily make it a bond, but you're starting to get at another idea. Why would you have negatives and positives? our electrons are shifting around. So what makes a chemical bond is that the electrons are shared between atoms. Okay? And we can look at varying amounts of sharing, but that's going to be another level. So what part of the electrons are going to be shared when we make this bond? The outermost, also known as the valence electrons. Or valence, I'll accept that too. Okay? Are all bonds the same? Why would we expect bonds to be different?
There's different elements.
The atoms are different. If the atoms are different, we would predict that the electrons that those atoms have are at different energies, which means our bonds are going to be at different energies. What's the problem with having different bonds? Same as the problem was of having different elements. We now have to name them. Okay? Thankfully, we don't have 118 different bonds. We just really have 3 to 4 primary categories. The two that we're really going to be primarily concerned about are ionic bonds, which are defined as the metal and a non-metal bonding with each other. Then we have covalent bonds, which are two non-metals bonding with each other. Okay? Are there other definitions? There's one for sure that should be relatively obviously missing.
The gas.
No. Gas is a phase for an individual compound. We have a metal and a non-metal, and then non-metal to non-metal. Metal to metal. Metalloids, interesting question on that. Those are probably going to be classified as your non-metals when we're looking at naming. But I'm not positive on that. I'll look closer. Okay. What happens if we have a metal-metal bond? What do we call that one? It's really original. Metallic. We have a metallic bond. Okay. Thankfully, we don't have to worry about those for 2 reasons. One, I don't have anything to tell you about it. And 2, it's not in the textbook. Less stuff to worry about. Okay. So those are good reasons. There is a third type of bond class that we will talk about later on. A covalent bond means equal sharing of electrons all the way through. Now, ionic bonds are unequal sharing of electrons. Okay? In fact, so unequal they're not sharing electrons. So we've got not sharing and completely sharing. That's pretty black and white. You think there might be anything floating through the middle? Yeah. We get something known as polar covalent bonds. Okay? How do we decide whether it's a covalent, ionic, or polar covalent bond? We could go based off of these definitions, but our polar covalent puts us in a gray area. It's all based on the difference in electronegativity. Okay? So the big announcement that we're going to end with right here